So this video is on first order linear ODEs, ordinary differential equations. So an ordinary differential equation is one where the eventual solutions, the functions that satisfy it, are going to be single variable functions. So you get an answer that is a single real variable and the domain is a single real variable. So you don't have any partial derivatives in there. So that's in contrast to partial differential equations, where you're looking at functions between higher order vector spaces of the real numbers. First order means that the only derivative that's going to appear is the first derivative. You're not going to have any higher derivatives. So you're just going to have the first derivative and the zeroth derivative, which is just y. And then linear is what makes these equations very easy. It means that y and dy by dx are only going to appear in the differential equation in linear form. Now they might be multiplied by some very complicated functions of x, but they themselves will be linear terms, so they won't be squared, for instance, they certainly won't be exponentiated, and they won't be multiplied together. So I'm going to write down now the general form for a first order linear ODE. So it's something of this form. So a, b, and c are going to be general functions of x. So a of x is some function of x times dy by dx, which I'll just write as y prime, plus b of x, again some general function of x, times y is equal to then c of x, where again c is some general function of x. So these could be very much so non-linear terms. However, this and this are appearing here raised only to the power of 1, so they're just appearing as themselves, and they're appearing linearly with respect to one another. So yes, they've got these coefficients that are potentially non-linear functions of x, but this is, if you ignore these and just consider these coefficients, then this is a nice linear equation in y and dy by dx. So that's where this linear comes from. And these equations of this form, have a beautiful method which allows you to solve them, providing you can integrate the necessary functions of x, and that is a big if, we can't necessarily integrate everything, but providing you can integrate the functions of x that you need to integrate in this methodology, then you will be able to solve differential equations of this form. There is a flawless methodology for this involving integrating factors. Now, people often write this in simpler form. We can divide through by a of x, and people usually will actually change the names of the functions that I've given here. They usually use p and q instead of a, b, and c. So more usually you'll see the general form of a first order linear ODE written like so: y prime plus p of x times y is equal to some q of x. And the way we've gone from that to that is, you can imagine just dividing everything through by a of x. Now that is slightly dodgy algebra, of course. We're assuming that for all x values, the multiplicative inverse of a of x exists. Now, in general, that won't be true. If a of x, for instance, was a function that's never equal to 0, so an exponential function, for example, then yes, it would be true. You can quite simply divide through by that with no concerns whatsoever, because the multiplicative inverse will always exist. However, in general, a of x won't necessarily not be 0 everywhere. So doing this is slightly dodgy algebra. You have actually put on the condition there that a of x is not equal to 0. So if you start with a differential equation in this form and you want to get it into this form, which we're going to need, which we often do in this methodology of integrating factors, when you divide through by a of x, you do need to think about, are there any actual roots to a of x? Are there any places in the real line, any x values for which a of x is going to be equal to 0? Because at those points, maybe this manipulation wasn't valid. Well, frankly, this manipulation wasn't valid. And you need to come back and think at the end, the solution that I've got from this new differential equation that came from doing this dodgy algebra, is it actually okay at those points? You need to check it in the original differential equation and also think about what's happening at those points where it's equal to 0 and make sure everything's okay. And very often it works, everything's fine. The overall thing that you get from this does satisfy the original one and works at these points, is okay. Or there's asymptotes and it doesn't matter anyway. But you do need to, when you do that, think this and think, I need to check at the end and think what's actually happening for these points and make sure that nothing dodgy has happened. But for all the other values of the real line where a of x was not equal to 0, then yes, it's true that you can do this, and the new differential equation that you get, which is of this form, will be completely equivalent to that original one. So this is the general form then that people usually write a first order linear ODE in. And what we're now going to discuss is how do you actually solve this. So to motivate this, I'm going to give some examples, or I'm going to give one example anyway. So we're going to look at this ODE, and this isn't actually in this form, it's actually in this original form, but it's going to give us the crucial idea that allows us to solve all these first order linear ODEs. So x, y prime plus y is equal to e to the x. Now, crucially, these linear ODEs where you have the dy by dx and the y term added to each other here, you cannot solve them by separation of variables. These are not separable. You can't get it in a nice separated form in general, where you can just solve it by reversing implicit differentiation. So a different strategy is going to be needed. And the crucial idea here is what's known as the concept of an exact equation. And this one that I've just written down is an example of an exact equation. And the way we're going to solve it is by noticing that this is actually the result of a product rule differentiation. This thing here, xy prime plus y, is what you would get if you differentiated x times y. Because if you use the product rule here, so differentiating this with the product rule, we differentiate this one first and we leave this one undifferentiated, and we then get this y term. So we'd have y, and then the other way around, leave this one and differentiate this one, you then get plus x dy by dx. So this differentiated gives you this. That's what is meant by this being an exact equation, because this term on the left, this linear term in y and dy by dx, is of exact form. And the whole idea behind how we're going to use this to solve these general ones is that in general, any first order linear ODE, you can get it so that this is something of this form, d by dx of some, I'll just say f of x times y, because when you differentiate this, you'll get f prime of x times y plus, and then leave the f undifferentiated dy by dx. So yes, we've divided through by the a of x to get it into this form, but if we go back to the original form over here, the whole idea is that you can always fix the differential equation, manipulate it so that it's in this form where you've got some coefficient in front of the dy by dx that is actually the undifferentiated form of the coefficient that's in front of the y, and then you can view this as the derivative of something of this form. And because you've only got the y and the y prime in linear form here, you're always going to be able to do that, and we'll show how you can do that later on. But for now, let's just go back to our more easy example where we've already got it in exact form here. So that's going to be what we'll do here. We're going to turn every single one of these into an exact form that can be manipulated like this. But let's go back to our example. So what we can now do is we can rewrite this differential equation as d by dx of x times y is equal to e to the x. And now that's in directly integratable form. So we can conclude from this that xy is just equal to the integral of ex dx, which is then just equal to ex plus c. So there then is the general solution to our original differential equation. So xy is equal to e to the x plus c. So now if you were given a starting condition, so you were told at some x what the y is equal to, then you'd be able to figure out what c needs to be equal to, i.e. you'd get your specific solution. And then you could, if you wanted to get your function in explicit form, you could divide through by x. You'd have to think carefully about what's happening at x is equal to 0 and make sure that it's okay to do this. Now, in the case of most of these solutions, the function isn't going to be defined at x is equal to 0. You can see that just from this line, because on this side, this is going to go to 0 at x is equal to 0. This is something that's positive, it's equal to 1 at x is equal to 0. So the only case where there's even a hope that this might be something that's okay to be defined at x is equal to 0 is when c is equal to minus 1. All the other values of c, there's no hope that it's going to be defined at x is equal to 0. There's no y that is suddenly going to satisfy it. Provided your c isn't equal to negative 1, you don't need to give this much thought at all. This is fine. If c is equal to minus 1, you need to think very carefully about what that means and whether you can define a logical, interesting value for y at x is equal to 1. So you would probably look at, if this was equal to minus 1, you'd look at what the limit of e to the x minus 1 divided by x is as x approaches 0, and I think by L'Hopital's rule that will be equal to 1. So the likely value that you would define y to be equal to is 1, so that you would end up with a continuous function. So in that case, you maybe wouldn't want to divide through by x, because then it would look as though the function couldn't be defined at x is equal to 0. But for all the other cases, it's never going to be defined for x is equal to 0, so you can quite happily do this manipulation. So another example now, and then we'll go on to the general first-order linear ODE of this form. So my next example is slightly more interesting. So we'll have y prime plus xy is equal to x. Now this is slightly more interesting because it's closer to this form that we've said we write the general first-order linear ODE in. So this is not an exact equation, so it can't be immediately turned into something like this, because if you might look at this and think, oh, it looks very like the previous one, maybe it's the same as this, but if you look at this derivative, this x is in front of the wrong term, so both of these are undifferentiated, and really here you've got the derivative of both of those, so you've got 1 is the derivative of x, and then y prime is the derivative of y, so it's the wrong way around. This was the form that was in the exact equation where you had non-differentiated, differentiated, differentiated, non-differentiated, so you had something that was the derivative of a product. However, for anything like this, and in general anything like this, there is a way that we can make it into an exact equation, i.e. something where you have a derivative of a product here. And the way we can do that is just by multiplying through by an exponential. So if we were, for instance, to multiply through by e to the x squared over 2, then this differential equation would become, and just go with this for the moment, you'll see why this is a clever thing to do. It would become e to the x squared over 2 y prime plus x e to the x squared over 2 y is equal to x e to the x squared over 2. Now, why is that a clever thing to do? Well, it's because if you differentiate e to the x squared over 2, so if we look at the derivative of e to the x squared over 2, and this is also a nice function to multiply through by because you know it's nowhere equal to 0, so truly you can go backwards and forwards in between these, so you could put a biconditional in there. They're utterly equivalent to one another, because if this is true, then yes, you can multiply through by this and it's still going to be true, so this is true. But equally, if you start with this, then you can go backwards because you can multiply by this thing's multiplicative inverse, which will always exist because this is never equal to 0. So they're truly equivalents. It's not a unidirectional equivalence as it was previously where we were dividing through by things that could have equaled 0. So this is a beautiful thing to multiply through by an exponential. So if we differentiate this, it will be e to the x squared over 2, chain rule here, times the derivative of x squared over 2, which is then just equal to x. So that's equal to x e to the x squared over 2. And now you see we've turned this into something of an exact form, because here, this is differentiated form, this. So we've got this undifferentiated, this differentiated, this differentiated, this undifferentiated. So now this is in an exact form. So this is equal to the derivative of y times e to the x squared over 2. So if you do this by the product rule, you will get that. So we now can write our original differential equation as d dx y e to the x squared over 2 is equal to x e to the x squared over 2. And we can then solve that by direct integration. So we'll get that y e to the x squared over 2 is equal to the integral of that. So integral of x e to the x squared over 2. So the antiderivative of that, well, just by inspection, we could do this by parts, or not by parts, sorry, by substitution. But just by inspection, we know that if we differentiate that, it gives us that. So its antiderivative is that. So this is equal to e to the x squared over 2 plus some constant c. So that's our general form of the solution. And now, without any qualms, we can multiply by this thing's multiplicative inverse because we know it's never equal to 0. So we'll then get that y is equal to 1 plus c times e to the, whoops, I've missed off a negative there, e to the negative x squared over 2. Which of course is a very, it's something in a very famous type of function. Things with this in e to the negative x squared over 2, they are bell-shaped functions. So similar to the normal distribution. This isn't quite the standard normal distribution because it's got a constant here and potentially the wrong coefficient here, but it's something of bell-shaped form. So it looks something like this. So now let's try and generalize this technique to our general first order linear ODE. So we have something now of the form y prime plus, and I'll just write p now, p is a function of x, times y is equal to q. So we want to multiply through by an exponential that is going to turn this into an exact equation. And going back to our example, our specific example here, the way we did it is by multiplying through by an exponential that had up here something whose derivative was this function here. Because then when you differentiate that exponential, you'll get it back again times the derivative of the thing in the exponent by the chain rule, and that will turn it into perfect form. So this is, in general, the general technique for turning a first-order linear ODE into an exact equation. So if you integrate p dx, so you get its antiderivative, and you take the exponent of that, that's going to be the perfect thing that we need to multiply through by. And this thing, this is called the integrating factor or the integration factor. I will probably call it the integration factor. So let's now multiply through our first order linear ODE here by this. Again, it's absolutely valid because this thing is never going to be equal to 0. So we can put a biconditional here. This is utterly equivalent to y prime e of this integral p dx plus p times e of the integral of p dx. And I might start calling the integral of p dx the antiderivative of p. Equivalent thing, but it makes more clear. It makes this somehow seem less scary. I mean, this looks hideous, but it really isn't. This is just the antiderivative of this thing down here, so that overall this is the derivative of this. Y is equal to q times whatever this is. And again, this is just some function of x. So p is a function of x. Once you anti-differentiate it, you'll get some function of x, and then you've just exponentiated that, so that's still a function of x. Now, you might get confused and think, which antiderivative should I use? Because, of course, if I anti-differentiate p, there's a whole selection of solutions. You know, there's the integration constant. It doesn't matter is the answer. You could use any of them. Just take the simplest one where the integration constant is equal to 0. You know, if you put on an integration constant of 2, all you've done is multiply through this entire equation by e to the power of 2, if you think about it, because if we had some c here, by the law of exponents, you can pull that out, and it's just e of this times e to the power of that c. So you could pull it out everywhere. So all you've done is multiply through by a constant, so it really doesn't matter. So just take the simplest one where the integration constant is equal to 0. It works for all of them. Take the simplest one. So there's our original first-order linear ODE, multiplied through by our integration factor, and now it's in exact form because this is the derivative with respect to x of y times this e to the power of the antiderivative of p. So that's equal to q e to the power of the antiderivative of p. So now you've got something that you can solve by direct integration. So just integrate this. This time you will need the general solution to the integral of that. So you will need the integration constant. And then you'll have that y times this function e to the power of the antiderivative of p is equal to that integral q e to the power of, the antiderivative of p. So that does look horrific, but this is actually a really beautiful technique which allows you to solve any first-order linear ODE that you're presented with, provided, of course, that you can actually perform these integrals. So first you're going to have to be able to integrate p to get an antiderivative for that, and then you're going to have to be able to integrate this thing here. So as long as you can solve those integrals, which is a big if, then you will be able to solve the first-order linear ODE. So we'll end there. Just before we do, I would just like to correct what I've written here. I have just taken the time and gone and looked up on the World Wide Web, and no, it's not called the integration factor, it's called the integrating factor. So that's the name for this thing that we're multiplying through by to turn our general first-order linear ODE into an exact equation. So thank you for watching. I hope you've found this interesting.